Alright, basic electronics. Alright, semiconductors. Materials that permit flow of electrons are called conductors: gold, silver, copper. Materials that block electrons are called insulators: rubber, glass, Teflon, mica. Materials whose conductivity between those of conductors and insulators are called semiconductors. Semiconductors are part-time conductors whose conductivity can be controlled. It shows the semiconductors with the MOHOs. Alright, your semiconductor 2. Silicon is the most common material used for the building of semiconductors devices. Si, or silicone, is the main ingredient in sand, and estimated that the cubic mile of seawater contains 15,000 tons of silicone. Silicone is spun and grown into crystallization structures and cut into wafers to make electronic devices. You see the silicone wafer as an seeded crystal boil molten silicone at 250 degrees, 25,070 degrees Fahrenheit. Alright, semiconductors. Atoms are pure and silicon wafers containing 4 electrons in outer orbit called valency electrons. Germanium is another semiconductor with 4 valency electrons. In crystalline lattice lace structures of silicon, valency electrons of every silicon atom in are located with a covalent bond with valency electrons of 4 neighboring silicon atoms. In pure form, silicon wafers do not contain any free charge carriers. An applied voltage across a pure silicon wafer does not yield electrons flow through the wafer. A pure silicon wafer is said to act as an insulator. In order to make a use of semiconductor devices, materials are such as phosphorus and boron are added to silicon to change silicon's conductivity. Your silicon atomic number is 14. Atomic weight is 28.064. Your valency of electrons, it has a 3 orbitals with 4 electrons on the outside. The single covalent bond of a silicon wafer. Alright, N-type. The pentavalent impurities is phosphorus, arsenic, actinium, bismuth, and have 5 covalent electrons. The phosphorus impurity is called silicon. Every pure phosphorus atom for 4 valencies electrons are located with a covalent bond with the valence electrons of 4 neighboring silicon atoms. However, the 5th valent electron of phosphorus atom does not find a binding electron, thus remains in free to float. The voltage is applied across the silicon phosphorus mixture. Free electrons migrated through the positive voltage N. The phosphorus is added to the silicon, is yielded above the effect that we say that silicon is adopted by the phosphorus, resulting in mixtures in N-type or negative charge carriers of silicon. The pentavalent impurities are referred to as donor impurities. Phosphorus has 15 count of 15 at 30 weight. 5 valency electrons on its last orbital, with the extra in the center of a silicon wafer. This N-type silicon electron flow shows the magnet through electron flow through a line or battery. Trivalent impurities: boron, aluminum, indium, gallium have 3 valency electrons. The boron is added to the silicon. Every boron atom through 3 valency electrons are locked up in covalent valence electrons are 3 neighboring silicon atoms. However, a valence spot of the hole is created within the covalent line between one boron atom and the neighboring silicon atom. The holes are considered the positive charge carriers. The voltage is applied with the silicon bearing mixture. A hole moves toward the negative voltage and the neighboring electron fills in its place. When boron is added, silicon is yielded above the effect, and we say that silicon is adopted doped with boron. The resulting mixture is called the p-type silicon, or positive charge carrier silicon. Trivalent impurities are referred to as an acceptor impurities. Your boron atom is 5 covalencies, 3 valence electrons, and a weight of 10.811 atomic mass. Alright, this shows a hole in the silicon wafer system, showing a positive flow on the electrons through a wire on a battery scope. The P2 type silicon 2, the hole on the boron atom towards the negative terminal of the electron. Neighboring silicon atom points toward the positive terminal. Electron neighboring silicon atom falls into the boron atom, filling the hole of the boron atom, creating a new hole in the silicon atom. It appears that the hole moves towards the negative terminal. Alright, a diode is two lead semiconductor that acts as one gate into the electron flow. The diode allows the current to pass in only one direction. Positive neutral junction diode is formed joining together the negative type and the positive type silicon. It is practiced the negative type of the silicon crystal is being grown, and the process is abruptly altered when the growth of the positive type of the silicon crystal. Finally, a glass or a plastic coating is placed around the joined crystal. The positive side of the anode and the negative side is the cathode. When the anode is cathodic, positive negative junction diode connected to the extra voltage, such as potential anode is higher than the potential cathode, the diode is to be forward base. And forward base diode is all allowed to flow over the device. When potential is an anode is smaller than the potential of the cathode, the diode is said to have a reverse base or reverse base diode current in the block. Alright, these are your this is a diode, positive and negative. Also the little picture with a symbol for a positive and negative diode. Water analogy of diodes. Alright, a spring, solid stop, movable plate, water type pivot. When water pressure on the left overcomes the restoring force of the spring, the gate is open and the water is allowed to flow through. When the water pressure is the right to the left, the gate is pressed against the solid stop and no water is allowed to flow. Spring restoring force is an analogous of 6/10 of a volt needed to a forward basis of a silicon diode. Alright, a diode, how it works. When a diode is connected to the battery, as shown in electrons on the negative side and the holes on the positive side are forced toward the center by electric field supplied by the battery. The electrons and holes combining, causing the current to pass through the diode. When the diode is arranged in this way, it is said to be a forward base. Alright, forward base shows the path of the battery going through the holes of the positive and negative, meeting in the center of the battery. Electrons negative. And repelling electrons in the electron holes, filling with the electron flow and the hole flow. Alright, diode, how it works too. The diode one-way gate feature does not work all the time. Typically, a silicon diode applied with a 6/10 of a volt greater is needed. Otherwise, the diode will not conduct the feature. It's usually forming a voltage-sensitive switch, or 1 through 4 characteristic silicon and germanium diodes is shown below. Alright, this shows the battery voltage in the way of the diode, the germanium diode and the silicon diode, 20 milliamperes. They're 0.5 to 1 volt. How it doesn't work. When a diode connected to the battery shown in the holes in the negative side of the force with the left side, while the electrons on the positive side are forced with the right, these result in an empty zone around with the positive and negative junction that is free of charge but carries creating a depletion of region. The depletion of the region acts as an insulator, preventing the current the flow of the diode. When the diode is arranged with this way, it is said to be a reverse base. Reverse base shows a closed door when both holes and electrons are forced from the center of the positive and negative diode and the track holes and the track electrons. Depletion region, reverse base, closed door. Diode application, half-wave rectifier. A diode converts an AC input into pulse DC output voltage. Whenever the input becomes negative in the diode's anode, the diode blocks current flow. The OP voltage becomes zero. The diode intrudes at 6 volt, drops in OP voltage of 6 volts, smaller than the IP peak. The OP frequency is the same as the IP frequency. So you have a rectifier going through current relay at the diode, showing the different peaks of the event, converting AC to DC output voltage. They're the same as the peaks. Diode application full wave rectifier. Full wave rectifier does not block the negative swings of the IP voltage, rather than transforms the positive swing at the OP voltage. To gain understanding the difference of operation following flow of the current flow with the pairs of the diodes and bridge circuit, it is easily seen with one pair of the DR3 out and D2 allows the current to flow for the positive VEE half cycle of V inches in. The other PD4 minus R out equals minus D1 allows the current to flow during to the VE half of the cycle of VE ends. OP voltage is 1.26 volts below the IP voltage peak. The OP frequency is twice the IP frequency. Alright, so you have all these little anode and cathodes going on, pretending the positive and negative connections at D1, D2, and D3, along with the rectifier. And your current voltage, like, shows that one's twice as much as the other. Alright, your AC-DC power supply. An AC2 DC power supply is built in using a transformer full wave rectifier. Transformers use to step down the voltage. IP rectifier converts the AC pulse to DC. A filter separate capacitor is used to smooth out the purpose pulses. Capacitors must be large enough to store a sufficient charge and to provide with a steady current supply to the load. The R load C is double greater than 1 times F, or F is rectified with a signal frequency. Alright, here is a transformer grounded with anodes and cathodes on it, and capacitor, resist, rectifier, and your voltage grounded frequency. Shows a ripple voltage out of the filter capacitor with load output with the filter capacitor. Transistor. Alright, a three-leaded semiconductor device that acts as an electrical controlled switch and the current amplifier. Transistor analogs the faucet. The turning faucet of the control knob alters the flow rate, water incoming out of the faucet. A small voltage current applied with the transistor could lead controls in a large current flow through its other two leads. Alright, this shows the transistor current in, current out voltage control leads with the water and water in control knob faucet analogy. Alright, type of transistor types: BJT, JFET, and MOSFET. Are bipolar junction transistor for JT, neutral, positive, neutral, and positive, neutral, positive. Junction field effective transistor, JFET, N channel or positive channel. Metal oxide semiconductor FET. Field effective transistor. Metal oxide semiconductor field effective transistor. Depletion type of the negative and positive channel. Enhancement type of the negative positive channel. As you see, the bijunctional transistor, the junctional field transistor, and the MOSFET, metal oxide semiconductor field electric effect transistor. Alright, the neutral, positive, neutral, and positive, neutral, positive. Neutral, positive, neutral is a small input current pulse voltage applied at the base and within voltage base and greater than voltage energy. Emitter. Allows the large voltage current from the collector to the emitter. A positive, neutral, positive, small output, negative voltage is based on the voltage base being over the voltage emitter, allows the much larger current to flow from the emitter to the collector. Or your NPN collector shows the collector base and emitter. The PNP shows the emitter in the base and the collector. Alright, the NPEVJT and how it works. When no voltage is applied with the transistor base, electron emitters are prevented from passing the collector side from the PN junction. The negative voltage is applied with the base and get even worse with the PN junction between the base and the emitter becomes the reverse base, resulting formation depletion region that prevents the current flow. Transistor off, voltage positive going through the base of the transistor, negative, positive, positive, negative side of the junction goes to the emitter into the ground electrons. How it works too, the positive voltage less than 0.6 of a volt is applied with the base of the non-negative positive negative transistor. The positive negative junction between the base and the emitter becomes a forward base. During the forward bias, escaping electrons are drawn to the positive base. Some electrons exist through base because the p-type of the base is so thin that onslaught electrons have leave the emitter to get enough into the collector side that they begin jumping into the collector, increasing the base voltage, increasing the emitter to the collector electron full. The recall positive current flow is the direction opposite to the electron flow. The current flows from the collector to the emitter. So the emitter goes from the electrons go through from the ground to the negative, positive, negative, and then go through the voltage, which is the conventional current flow depletion regular vanishes in conventional flow electrons. The BJ water T analogy. Negative, positive, negative J base times voltage emitter, and positive, negative base is less than voltage emitter. Shows a collector current going through 2 volts and to the gateways. Water analogy from the base on the current and the collector current, emitter current. It's electrical base symbol. Negative, positive, negative transistor complete circuit normally off, no current paid. This is the collector on the emitter when the base is not activated. Zero base current at positive, negative 1/5 volt. No gate. The gate is closed. Open. There's the relay with the a negative, positive, negative. Basically, a current zero collector, another battery, 2 diodes, and a transistor. The negative positive transistor complete circuit is when the voltage base is greater than the voltage emitter, we have an operating circuit. When the current base is the collector of the emitter when the base is activated. This shows the voltage positive and the negative positive voltage going through a rectifier, through a diode to the positive side, through the P and N side of the emitter and the collection side of the diode, a large collection current. Transistor experiment LED on and off, turn off switch on and off switch for the LED. This shows the LED rectifier and going through a regulator kind of capacity, current, gate, battery voltage. Alright, junction field effective transistor for the BJT3 lead semiconductor device. GFET is used for electronically controlled switches, current amplifier, voltage controlled resistors. Unlike BJTs, JFETs do not require bias to control or current controlled by using a voltage. JFETs normally use the voltage generator with the voltage VSVS. There are 2 types of GFET, the N channel and the P channel. In the N channel, the JFET voltage emitter voltage is at the gate of the voltage gateway and the voltage switch. Reduces the current flow for the drain source and then operate the voltage drain voltage source. Voltage voltage drain is greater than voltage source. In the P channel, the JFET at the voltage emitter, the voltage applied to at the gate of the voltage gate and the voltage switch. Voltage is greater than the voltage gate, then reducing the current from the source. The operates the voltage source is greater than the voltage drain. The GFT's high input impedance draw little no important current. The arrow shows that there is any circuit component controlled connected with the gate of the JF with no the joint field entrance transistor current away from sunken into the circuit. Alright, the N channel shows the from the thing going into the gate through the source and the drain. Also, for a positive train, the drain and the source goes out through the gate. Your metal oxide semiconductor field effect transistor similar to the joint field effect transistor metal oxide inside later placed at the gate to obtain the high input impedance at the gate and the gate input impedance upon 14 ohms. The use of insulator described above yield the load gate with the channel capacitation. Too much of the static electricity builds up on the gate and the MOSFET may be damaged. MOSFET types. Enhancement type. Normally off those no current flows for the drain source of the channel with the voltage gate is equal to the voltage source. The voltage applied at the gate causes the voltage gate not equal to the voltage source of the drain source, which channel reduces the resistance to the flow. Depletion type. Normally, thus, maximum current flow for the drain source and channel of the voltage is equal to the voltage source. Voltage applied at the gate, the voltage gate is not equal to the voltage source. The drain source channel increases the resistant current flow. This shows the enhancement MOSFETs for the gate drain Gorson salt source of the N channel and P channel. Current inflows are voltage gain over the source and voltage gain less than voltage source. And the depletion MOSFET, you see the gate with a drain source, but it's complete. The N channel is connected to the drain the source with an arrow flowing through it. Voltage gain is less than voltage source. And when the drain goes through the source, is the P channel voltage gain is greater than voltage source. Alright, optoelectronics. In the optoelectronics, we deal with two types of electronic device. The light-emitting device is one of that generates electromagnetic energy under the action of the electric field. Example, the light-emitting diodes, visible infrared lights. Light-detecting device is one that transforms electrical energy into input into electrical current voltage. Example, the photoresistors, photodiodes, phototransistors, etc. You have a light-emitting diodes, infrared detector, light-emitting diode, LEDs, LED 101. Two semiconductor devices, light emitting the positive and negative junction diode, visible infrared, has polarity, recalls the diodes at each one gate to the current flow. A forward-based positive and negative junction diode allows the current to flow in the anode to the cathode. And an electrical emitting device emits light, and the anode is more positive, approximately 1/4 volt, 1.4 volts, than in its cathode. The reverse LED stops conducting, emitting light. This shows the cathode shorter leg and the anode longer leg of the flat LED. Similar diodes, the LED is currently dependent on the device. The LED brightness is controlled by the control current with the LED. Too little of the control through the LED and makes the LED remain off. Small currents of LED dimly lit in the LED. Large currents of LED brightly light in LED. Too much current through LED is a short. A resistor placed in a series of LEDs accomplishes current control. The anode and the cathode shows the LED symbol with a or LED 1013. Let the volt sources supply voltage. Let the L voltage of the force-based voltage for the LED. Let 1 be the desired current from the flow from the LED. Then current limiting the resistance of the R is the size of the voltage. The voltage regulate resistance equals the voltage source down the voltage forward. The resistance is equal to voltage resistor divided by desired current flow equals to the voltage source minus the voltage forward minus the desired current flow. If R is chosen smaller than above the value, the large current will flow through the LED. The LED can hold only a limited current, varies from 20 milliamperes to 100 milliamperes. If the current through the LED is larger than the maximum allowed light value, the LED will be damaged. This shows the voltage source going through the resistor limit currents of the desired current flow and the voltage VR and the voltage in the voltage field with the light in the LED. Alright, visible light LED, an expensive durable tip, typically used indication of lights colors common green, yellow, orange, and red. Maximum forward voltage 1.8, approximately 1.8 voltage. Typical operating currents 1 to 3 milliamperes. Typical brightness level 1 to 3 MSCDs or 1 milliamperes or 3 MCDs or 2 milliamperes. High brightness LEDs exist. High brightness flashers and bicycle flashers. Miniature jumbo shows the blinking LED containing miniature integrated circuits that cause the LED to flash from 1 to 6 times a second. Typically used in indicator flashes, may also use in simple oscillators. All right, your tricolor LED. To the LED placed on the pair wall facing opposite directions. One LED is red and the other or orange. The other is green. Current flow with one direction. Turn one LED on, with the other remains off due to the reverse bias. For current flow with one other direction, turns the LED off and the second LED on. Rapidly switching the current flow of the direction alternately to the LEDs on the given yellow light using a polarity indicator. Maximum voltage rating 3 volts. Operating range from 10 to 20 milliamperes. These shows the green and the red cathode, the red and the green LED, tricolor LED light. Alright, your S7 segment LED display. Used for displaying numbers and other characteristics. Seven individual LEDs are used to place in the display. Voltage is applied with only one of the LEDs. A portion of the 8 lights light up. Unlikely like liquid crystal display LCD or 7-segment liquid light emitting diode displays tend to be more than rugged and then consuming more power. Alright, here is your LCD liquid crystal display LED deployments with an 8 segments, common cathodes, anode connections, common cathodes. Light emitting section of the LED is made joining the N type and the P type of the Sunday connectors with a positive and negative junction. The positive and negative junction is forward-based electrons in the northern negative side, excited expressed with the positive and negative junction in the positive side where they combine with the holes. As the electron combines in the holes, the photons are emitted. The positive and negative junction section of the LEDs encased with the epoxy shall be doped with light and scattering particles, diffusing light, making the LED appear brighter. Often a reflector placed beneath the semiconductor is used to direct the light upward. It shows the positive and negative coming through the light emitting diode at the photons and holes in electron positive and negative section or PN junction. Also shows the LED epoxy LED chip reflectors and the cathode anode protection. Photoresistors. Light sensitive variable resistors. The resistance depends on the intensity of the light incident upon under dark condition. Resistance are quite high to the mega ohms, called dark resistance. In bright conditions, the resistance are lowered, fewer 100 ohms. Responsible time, the photoresistance is used to the light. It takes a few milliseconds before it lowers its resistance. Photoresistor experience removal of light and may take a few seconds to return to darkness. Your symbol for a photoresistor is a current going through a circle with two lines of electrical paths headed towards it. Some photoresistors respond to light and contain photons with a particular wave of the spectrum. Example, cadmium sulfide photoresistor responds to light within 400 to 800 negative nms range. See, lead sulfide photoresistors respond to infrared light. Alright, special resistors, special semiconductor crystals such as cadmium sulfide left side light is used to make photoresistor when semiconductors display for the dark electrons, but the structure resists for the flow of the resistor becomes too strongly bonded to the crystal atoms. When the semiconductor is eliminated, incoming photons light concluded with the bond of the electrons, stripping from bonding atoms, creating the hole in the process. Liberated electrons contribute the current flow through the device. Or you have your electron metering through a positive negative diode, cadmium sulfide, summoned the conductor hole created with the conventional current flow, actual package, and photons. The photoresistor application light activity relay. Light sensor voltage divider into the used trip relay whenever light intensity changes. Light activity activated circuit. The photoresistor is exposed to light resistance. Decrease the resistor base current with the voltage. Increase the base current with the voltage large enough that the collector emitter pair of the transistor conductor triggering the relay. The value of R1 in the light activated with the circuit should be around 1 kilo ohm, but maybe have adjusted. Dark activated relay works in similar opposite manners. The R1 is dark activated circuit of 100 kilo ohms, or may have all been adjusted with a 6 to 9 relay volt with 500 ohm coil on it. Can be used in either circuit. Your light activated relay shows the resistor 1, resistor 2, the light photoresistor cell, the positive negative reflector with a diode and a current coil, iron coil, and a light activated relay. Your light activated relay with a positive negative and two resistors, a rectifier, or a diode, and negative positive 9 volts. Alright, your photo died in two less lead semiconductor provide and transfer light energy to electric current. Supposed anode and cathode photodiode are wired in current meter. When the photodiode is placed in the dark, the current meter displays zero current flow. When the photodiode is exposed to light, acts as a current source, causing the current flow from the cathode to anode photodiode through the current meter. The photodiodes have very linear light versus current characteristics commonly used light meters and cameras. Photodiodes often built in lenses, optical filters. Response time of the photodiode slow the increase the surface area of the photodiode sensitive to the photoresistor. Your symbol for your photodiode is like this. Your photodiode has an N-type semiconductor sandwich with a positive type semiconductor. The negative side of the cathode, the positive side is the anode. Upon illumination, the number of photons passing through the negative side into the positive side of the photodiode. Sometimes sometimes photons make it into the positive side, collide with the bound an electron with the positive semiconductor, ejecting them into the creating hole, and then them and creating holes. The collision are closed in the positive and negative junction and ejected by the electrons, causing the junction electrical electrons on the negative side and extra holes on the positive side, segregating the voltage voltage energy and negative voltage energy charge to leave with the potential difference across the positive and negative junction. When a wire is connected between the cathode and anode, the conventional positive current flows from the anode to the cathode. So, are your photodiode electron application and photovoltaic current sources? Photodiode current light energy directly into electrical current that are measured with a meter. The input intensity light and output current are nearly linear. Here is your photodiode with a current meter and your brightness light. Solar cell. Solar cells are photodiodes with very large surface areas. Compared with the photodiodes, large surfaces of photodiode of solar cell yields a device that is more sensitive to incoming light. The device should yield more power. The large current volts. A solar cell yield more power. A single cell solar provide with a 0.5 that can apply up to 1/10 of an ampere when exposed to brightness. It shows a solar cell looks like a negative battery with a circuit with and a diode. Solar cell. Alright, your solar cell basic operation power sources. Each solar cell produces an open circuit voltage from around 0.45 10 hundredths or to 5/10 of a volt may be generated with 1/10 of an ampere bright light. Similar to the battery, solar cells can be combined in a series of parallel and adding cells in the series yields the output voltage that is sum of the individual cell voltages. Adding solar cells in parallel yields increasing output current visa and visa versus visa single solar cells. Alright, a solar cell basic operation battery charge. 9 solar cells placed in series can be used with a recharge of 1.5 volts of the nickel-cadmium cells. The diode is added to the circuit to prevent the nickel-cadmium cells from discharging through the solar cell during the time of darkness. It is important not to exceed the safe charging rate of the nickel-cadmium cells. To slow the charge rate in the resistor can be placed in a series of batteries. Alright, phototransistor is a little sensitive transistor. One common type of the phototransistor is the base layer with the BGT replaced with the light sensitive surface. The light sensitive surface at the base of the kept in the darkness of the collector emitter period of the BJT does not conduct. Light sensitive surface A with the base exposed to light and a small amount of the current flow for the base emitter. The small base emitter controls the large collector emitter control. Alternatively, one can also use the field effective phototransistor or photo FET field effective transistor. In the field effective transistor, light exposure generates a gate voltage which controls the drain source for current. You have your phototransistor and then a photo field transistor, drain and source collector and emitter. Alright, how phototransistors work. Bipolar phototransistors resemble bipolar transistors. They extra large positive type of the semiconductor region open for the little exposure. The photons from the light sources collide with the electrons when the positive type of the semiconductor then goes in the energy jumping across the positive negative jumping energy battery provided with the photons are bright at the frequency energy. As electrons jump with the positive region into the lower negative region, holes are created with the positive type of the semiconductor. The extra electrons injected with the lower negative type of the slab are drawn toward the positive terminal of the battery, which electrons with the negative terminal of the battery are drawn with the upper negative type of semiconductor and across the negative positive junction, which combines the holes, and the net result is an electron current that flows from the emitter to the collector. Shows the photons, the holes, and the electrons going through the electrical flow through the electrical meter through the positive negative battery collector and emitter. Phototransistor application light activated relay. A phototransistor is used to control the base of the current supplied with the power switching with the transistor. They use to supply the current to the relay. When a light comes into contact with the photoresist, the phototransistor turns on all the way and current to the path of the supply with one base of the power switching transistor. This allows the power transistor to turn on current flow through the relay, triggering into the switch states. A 100K pot is used to adjusting the sensitive device for controlling current flow through the phototransistor. Alright, this shows you your phototransistors, rectifiers, transformer, ground, and your relay, gate relay. Or light emitting relay. Phototransistor application dark activated relay. A phototransistor is used to control base current with the supply with the power switching transistor that is used to supply the current to the relay. When the light is removed from the phototransistor turns off, allowing more current to enter the base of the power switch transistor. This allows the power switching transistor to turn and current flow through the relay, triggering it into switch states. The 100K pot is used to adjusting sensitive devices controlling current flow through the phototransistor. Phototransistor relay, the diode, phototransistor diode relay, blah blah blah, current. Alright, your phototransistor application tactometer. The phototransistor is being in a frequency counter of the tactometer. A rotating device connected with the rotating shaft. The rotating device has one hole in it, and for the given setup, the disc will allow the light to pass through the hole once every revolution. Light passes through the disc, triggering the phototransistor in conjunction. The frequency counter is used to count the number of electrical pulses generated back. So you have a light source, a rotating disc with a hole in your photo transistor with a voltage battery and a resistor and on the line to frequency counter. That concludes basic electronics. No publisher notice noted.